Okay, so let's start with another exercise, that is heart disease prediction. So this is to predict any person who's going to have this kind of a problem, that is heart disease. So let's first clear all the outputs, and then we will start working on this. So we can see that all these processes have been cleared, and the heart disease prediction is the objective. In this exercise, we are going to use the machine learning in predicting the heart diseases. Such warnings, if predicted well in advance, can provide important insights to doctors, who can then adapt their diagnosis and treatment as per the patient's whatever is the condition of the patient, right? So that is the objective. So we can run this. Then the algorithm used here are included K nearest neighbors classifier, then support vector classifier, decision tree classifier, and random forest classifier. The data set has been taken as from Kaggle, that is again a source. Now the objective of doing this using four classifier is that whatever gives, which of the option gives the best option, best classifier, that we are going to use. That is why we are considering these four algorithm, that is K neighbors, then support vector, and decision tree, and random forest, right? Now for doing that, as usual, we have to import our libraries, pandas, numpy, matplotlib, and of course all these things we are going to import. So it is going to be import all this. Then warnings also, simple filters, then there are some other sub libraries also which are there. So all these things are required, and all these are imported, right? Then we are going to import some other libraries like sklearn. Then within that all other sub libraries like pre-processing, neighbors, svm, tree, ensemble, etc. So all those can also be imported, so that we can use it as and when we want it. We are also going to have our data set to be loaded onto this data frame, that is df, and this df we are having this is a CSV file, as you can see here, and we have the data as the heart underscore data -1 CSV. This is the data file, and header is none in this, right? And this is the complete path of the data file. This is available on this location, right? So we can run this also, so that our data comes into our and working. So we can load that. Then we are going to have all the columns which are there. So df columns will give you all the columns which are there. So this has age, sex, CP, etc. All these things are there. Then we are going to have the top 5 rows that you can get: age, sex, CP, test BPS, cholesterol, probably FIB, ABS. All these things are there. Whatever the columns are there, all of them which are already mentioned here, you are getting all these columns here in the top 5 rows data. Then we are also getting the shape of the data, that is the rows and number of rows and columns, that is 303 rows and 14 columns. Info also you are getting, that is the the type of data that it has, integer or float or object or whatever, that also you can get. Then as you can see from the output above, there are a total of 13 features and total and one target variable. Also there are no missing values, so we don't need to take care of any null values. So in case you are sure that your data is perfect, there is no need to go for that. But if you have doubt, definitely you must go for this. So we can run this, nothing is going to happen. Then we are going to have the details of the data. That again is something like a statistical analysis, which gives you count, mean, standard deviation, all these things. Then the method revealed that the range of each variable is different. The maximum value of the age is 77, and for cholesterol it is 564. Thus feature scaling must be performed on the data set. So it depends. That is why the knowledge of your data is very important. You must be knowing not only about the data, but also the domain knowledge, the purpose of doing all that. That is also important. That is also helpful, in fact. So we can go for this. Then understanding the data, we are going more into details. So we are going for correlation matrix. That is, to begin with, let's see the correlation matrix of features and try to analyze it. In the figure size is defined as 12 by 8 by using RC parameters. Then we used pie plot to show the correlation matrix. Then using X ticks and Y ticks, we have added names to the correlation matrix. Color bar shows the color bar for the matrix. So we can run this, nothing will happen, but definitely here we are going to have this. So this, and for that we have got this code. RC parameter figure fixed size is 20,14. Mat show DF correlation, then Y ticks, NP arrange DF shape 1 and DF columns. Similarly X ticks, NP arrange DF shape and then DF columns, and then plot color bar. So we are going to have a color bar here with the help of this. So you can see that a good heat map gets generated, which is giving you all those required, and we can also draw our understanding about the correlation. What is the kind of correlation between different variables which are there. Like you can see, all those features that were there are available both on the y-axis and they are also you can see it on the x-axis also here at the top, right? So these are quite useful details, and we can definitely get more and more understanding about the data. Right now we are going for, it's easy to see that there is no single feature that has a very high correlation with our target value. Also some of the features have a negative correlation with the target value and some have positive. So we can run this, nothing will happen here. Now we are going to import Seaborn also, because we may need that. So we can have the correlation matrix, and DF is the correlation for this particular data frame. Top correlation features, correlation matrix is index, PLT figure fixed size is 2020, and then plot is the heat map. G is equal to SNS heat map, DF top correlation map features, then correlation annotation is going to be true, and map is going to be RDY because it's a different color, that is red, yellow and green. So that is why it is the short name of that individual colors. So you can run this and you can get a good heat map. It is still under process. Yeah, here you have got this, that is red, yellow and green color which is mentioned, is all there with the annotation also present in this. So you can see that this way you can definitely get a good information, and you can definitely understand your data much better. Right now we are going to write this code for, like is there any null value or anything which is null in the data. So df is null dot sum, target map, these are the various column that we are considering, then sex, then thallium, CA, say fill NA, all this, whatever is required. I mean we can write or remove whatever we want. Then importing matplotlib pyplot as PLT and Seaborn. So we already imported it, but it is better to import it again, so that in case it doesn't have, then you may get an error. So we can go and run this. So when we run it, you are going to nothing will happen, because here we are not plotting anything as such. It is only thing that this processing has been done, right? Then we are going to create a cat plot, and here for that we have written the code like sns.catplot. Kind is count, data is df where we have got the data, x is the age, hue is target, order is of course a data frame age, and sort values unique, right? Then title is variation of age for each target class, and we are going to plot this thing. So once we give this run this command, then you are going to get a variation of age for each target class. This is a kind of a bar chart that you are getting based on the age count, and the target is 0 or 1, right? So this is how you can get this kind of a plot, right? The next is that now we are going to get a kind of a histogram. So the best part about this type of plot is that It just takes a single command to draw the plots, and it provides so much information in return. So you can use that. Then you can draw this. This is the way, df.hist. You are going to get these details, array, and then all those details that you are going to get. And then along with that, you are also getting the graphs, histograms, right? So, and you can see that all these things are available just with the small code, that is df.hist, because the data has already been transformed into this with this kind of a code. And the same data is used here for the purpose of creating this, and for different kind of features that we have seen. If you go back and see your output for the head or etc., you will see that all these the features, age, CA, cholesterol, CP, all these things are already there, and on the basis of that we are getting a kind of a category plot. What is the kind of a category and different types of histogram that you are getting here, right? About 4 plus 4 plus 4, 12, about 13, all whatever number of variables were there, all those variables you are getting a histogram, right? So this is again a very informative, and the person who is having the knowledge of coming from the medical background or heart disease expert, he can definitely infer it properly. So let's take a look at the plots. It shows how each feature and label is distributed along different ranges, which further confirms the need for scaling. So now you can see that all these are available in histogram, and we are going to just by looking at it, we can draw our inference that it shows that how much feature and label is distributed along different ranges, which further confirms the need for scaling. The scaling means that you can increase or decrease the scale part. So next, wherever you see discrete bars, it basically means that each of these is actually a categorical variable. We will need to handle these categorical variables before applying machine learning. Our target labels have two classes, 0 for no disease and 1 for disease, right? So this we can run. Then we are going to create a bar plot for target class. It's really essential that the data set we are working on should be approximately balanced. An extremely imbalanced data set can render the whole model training useless and thus will be of no use. So let's understand it with an example. So balancing of data is very important, otherwise all the efforts will go futile. So let's say we have a data set of 100 people and with 99 non-patients and 1 patient. So that means it is not balanced, right? So this shows that if you're in your data set of 100 patients or 100 people, 99 non-patients and 1 patient, without even training and learning anything, the model can always say that any new person would be a non-patient automatically, because the data is not sufficient, and have an accuracy of 99%. However, as we are more interested in identifying the one person who is a patient, we need balanced data set, so that our model actually learns, because we have to learn. I mean, there is no magic in this. Only thing that you have to train the machine with the help of your data only. So data should be adequate, should be sufficient. So that is what we are going to do with this, running it. Then for x-axis we use the unique values from the target columns and then set their name using x-ticks. For y-axis we use value count to get the values for each class. We colored the bars as green and red. So this is again for our information. Now we are going to write the code for this. That is RC params, figure fixed size is 8 by 6, PLT bar, DF target, that is our target. Then unique DF target, value count, color is equal to red and green. Then PLT x ticks 1, 0, x label target classes, y label count, PLT title is going to be count of each target class, right? So we can run this and see you are getting a count of each target class, and as the color we have already mentioned here, red and green, we got this in this, and that is how you can have the target classes and the count, right? So that is how you can keep on getting more and more information about your data set. Now SNS set style wide grid, SNS count plot is equal to target, data frame is DF, and palette is red, blue and red, blue and I think orange. So you can run, right? So you can get this kind of a plot here with the help of this code that we have seen. And again you can, it's the same kind of this. Now you are getting a different color, that's it. So there is not much of a difference. Now from the plot we can see that the classes are almost balanced and we are good to proceed with the data processing and wrangling, suit, right? So now data wrangling we can do with the help of this data. To work with the categorical variables, we should break each categorical column into dummy columns with ones and zeros. Let's say we have a column gender with values 1 for male and 0 for female. It needs to be converted into the two columns with value 1 where the column would be true and 0 where it would be false. Take a look at the gist below, right? So we can run this, we can nothing is going to happen. Now we need to get dummies from pandas. Next we need to scale the data set, for which we will use the standard scaler. The fit transform method of the scaler scales the data and we update the columns. So we are using standard scaler for this. Again is a library available in the scaler. So we can run this also, nothing is going to happen. Now we are going to write this code for this purpose, that is df pd get dummies, df columns sex cp fbs, all those columns that you have seen, cp fbs, rest ecg exchange, all those things you are getting. And this is what we are going to, with this code it is going to be scaled. Standard scaler is equal to standard scaler. Then columns to scale, age, these are the columns to be scaled, and df columns to scale is standard scaler dot fit. Then we are going to fit it. We are going to fit it and transform into the columns to scale, right? So this is the code which is helping us to scale the data set. So now we are running it and this job will be done with this. The data set is now ready. We can begin the training our model. Now the data has been scaled up and we can go for developing our model or with the help of the training part, right? So we can do that. Now we are going for machine learning, since we are working for with 4 different approaches, as we have already discussed in the beginning. We took 4 algorithms and the variables there were various parameters and compared the final models. We split the data set into 67% training data and 33% testing data, right? So this again is clear that this is how we are going to do our training and testing. Now with this code we are going to divide or split the data set, that is y is equal to df target, x is equal to df drop target, axis is equal to 1. And then x train, x test, y train, y test, train test split, xy test side is equal to 0.33 and random state is equal to 0. That means there is no iteration in this. So this is how we are going to split our data set into 67% and 33%. Now we are going to run this. Now next we are going to apply our algorithm. Now k neighbor classifier is going to be used. That is our first algorithm. This classifier looks for the classes of k nearest neighbor of a given data point, and based on the majority class, it assigns a class to this data point. However, the number of neighbors can be varied. I varied them from 1 to 20 neighbors and calculated the test score for each class. So here, this is again for our understanding. KNN scores is equal to for k in range 1 to 21. Right, this is the range that we are considering for this, and KNN classifier is equal to k nearest classifier n neighbors, right, is equal to k. So k is a number that is going to increase 1 by 1 from 1 to 21, and KNN classifier is to be fit into X train and Y train. This is the code that is for doing the classification. And KNN scores, append KNN class classifier score is equal to X test and Y test. So this is what will do our KNN classifier, right? So we can run this, and once we run this, you can see that the job is completed. Then we will plot a line graph of the number of neighbors and the test score achieved in this, right? So that also we can do. Of course nothing will happen here, but here we are going to plot the graph, and this is with the help of this code, that is plt.plot k for k in range 1 to 21, KNN score color is equal to red, for I in range 1 to 21, for I in range 1 to 8 also. And then this of course is a remark, so here we are writing the code. plt.text I KNN scores I minus 1, I KNN scores I minus 1, and then plt xtix for I in range 1 to 21, and X label number of neighbors, and Y label scores, and title is K neighbors classifier score for different K values. So with this code we are going to get a plot, and that will definitely be, yeah, this is the kind of plot that you are going to get. Number of neighbors are here, that is K, and the scores are here on this. So you can see that the title is coming as K nearest neighbor, scores of different K values. So this is how you can plot this particular graph. So as you can see, we achieved the maximum score of 87% in this, right? Here you can see that the maximum score that you have got is about 80, something like this. So it's around 87%, right? The next that we are going to, this of course we can run here, run, nothing is going to happen. Now we are going to use the support vector classifier, another algorithm, and this classifier aims at forming a hyperplane that can separate the classes as much as possible by adjusting the distance between the data points and the hyperplane. There are several kernels based on which the hyperplane is decided, and we tried 4 kernels, namely linear, poly, RBF and sigmoid. So again, these are the things which you must have gone through the SVM when we discussed about the SVM tutorial, support vector machines. Now we are going to use this code for doing this. So SVC score is equal to, this is where we are going to have this. Kernels is linear, poly, RBF and sigmoid. And for I in range len kernels, SVC classifier, SVC kernel is equal to kernels I, SVC classifier fit X train, Y train, SVC scores append SVC classifier, score X test, Y test. This you must have seen the code earlier also. So we are going to run this, and once we run it, we are having the scores also in our SVC score. Once we had the scores for each, we use the rainbow method to select different colors for each bar and plot a bar graph of the scores achieved by them. So we can run here. Again we are going to plot the graph. Now colors is equal to rainbow, NP line space 1, length is kernel, PLT bar kernels is equal to SVC scores, colors is equal to colors, for I in range len kernels, PLT text SVC scores, then X label is kernel, Y label is score, and title is support vector classifier scores for different kernels. So we can run it and see that we are going to get a colorful kind of a bar graph. Support vector classifier score for different kernels. This is the score, and here are the kernels, and these are the 4 algorithms that we have used: linear, poly, RBF and sigmoid, right? So that is how you can get this kind of a bar chart, and this is another algorithm which we have used as support vector classifier. As can be seen from the plot above, the linear kernel performed the best for this data set, achieved and to secure 83%, right? So you can see that we have got this about 83% here, right? So this is how we can do this. So we can run this. Now we are going to go for the decision tree classifier. Now this classifier creates a decision tree based on which it assigns the class values to each data point. Here we can vary the maximum number of features to be considered while creating the model. I range features from the 1 to 30 to the total features of data set after dummy columns. We can run this, nothing will happen, but DF score is equal to DT score is equal to decision tree score is equal to, of course here we are going to have the score for I in range 1 length x columns plus 1, increase 1 by 1, then DT classifier, decision tree classifier, maximum feature is equal to I and random state is equal to 0, that is no, and then that means we are going to increase, that is as for I in the range from 1 to length, whatever length is there, right? Then DT classifier fit, we are going to fit this as X train and Y train, and DT then we are going to append this DT score append DT classifier, and then we are going to get this score. We can run this. Now once we have the scores, we can then plot a line graph and see the effect of the number of features and the model scores. So we can run this, nothing will happen here. Then we are going to plot a graph with the help of this code, that is plt.plot I for I in the range 1 to length x dot plot columns plus 1. Actually the codes are by and large similar. So DT scores is equal to color is equal to green for I in range 1 length x dot column plus 1. PLT text DT score is like this, I and DT score is equal to I minus 1. Then PLT x text for I in range 1 to len x columns plus 1, and then PLT x label max features, PLT y label scores, and title is decision tree classifier score for different number of maximum features. And then we can run this. So once we run this, you can see that you are going to get another plot with the help of this. It's a quite zigzag kind of a graph that we have got in the decision tree classifier, and of different number of maximum features, right? So you can see here that from the line graph above we can clearly see that the maximum score is 79%. You can see here, this is the way it goes to this 79%, yeah, right? So 79 is the highest percentage here, right? So we can run this also, nothing is going to. Now we are going to use the random forest classifier. This classifier takes the concept of decision trees to the next level. It creates a forest of trees where each tree is formed by a random selection of features from the total feature. Here we can vary the number of trees that will be used to predict the class. We calculate test scores over 10, 100, 200, 500 and 10,000. These are the trees, right? So we can run this, nothing is going to happen. Now we are going to use the RF score is equal to blank, then estimators 10, 100, 200, 500, 1000, and again you see the code is again similar, but of course the approach is different. For I in estimators, a random forest classifier estimators is equal to I, random state 0, RF classifier fit X train, Y train, RF score append RF classifier scored X test, Y test. So we can run this. Of course nothing, we are not getting any output in this, but certainly we are going to have. Now next we plot these scores across a bar graph to see which gave the best result. You may notice that I did not directly set the X values as the array 10, 100, 200, 500, 1000. It will show a continuous plot for 10 to 1000, which would be impossible to decipher. So to solve this issue, I first used the X values for 1, 2, 3, 4, 5. Then I renamed them using X ticks. So we can run this. Of course nothing happened because this is now we are going to draw the plot. Colors of course is going to be rainbow, then NP line space, and length is estimator. Whatever estimator's value is there, the same is going to be the length of this. And PLT bar I for I in range len estimators, RF scores, color is equal to colors, width is 0.8. You can change the width if you want. Then for I in range len estimators, plot PLT text I, RF scores I, RF scores I. And then PLT x ticks is equal to 1 for I in range, len estimators, and labels is equal to string estimator for estimators in estimators, right? Then X label number of estimators, Y label scores, and title is going to be random forest classifier score for different number of estimator. So this is again we can run and we can see that what type of graph that we are going to get. Now here we are getting again a very good colorful graph, bar charts, random forest classifier scores for different number of estimators. This gives us that different, this is the score and this is the number of estimators. So we can get 79, 84, 83, 84 and 83. So with the help of this, now you can say that taking a look at the bar graph, we can see that the maximum score is 84%, like here 84%, right, was achieved for both 100 and 500 trees, right? So for 100 and 500 trees we have got this maximum highest score is 84%, right? So we can run this also. Then the conclusion that we can have from this is the exercise involved analysis of the heart disease patient data set with proper data processing. Then 4 models were trained and tested with maximum scores as follows: K nearest neighbor 87%, support vector classifier 83%, decision tree classifier 79%, and random forest classifier is 84%. So the K neighbor classifier scored the best score of 87% with 8 neighbors, right? So this is how we can say that yes, we have got this kind of a outcome, and we can decide that yes, this is the best approach for this. Thank you.